And now I have the pleasure of introducing KIPAC graduate student Anthony Flores, who is going to be telling us all about cosmic chemistry and what current and future generations of X-ray satellites can tell us about enrichment in clusters of galaxies.
Thank you. Yes, I'm Anthony, fifth-year grad student, working with Steve and the rest of the XOC team on X-ray measurements of galaxy clusters. And over the next couple of minutes, I'll try and give some insights into the question of when and how the universe was enriched with heavy metals. So galaxy clusters, as the most massive gravitationally bound objects in space, trap almost all of the baryonic matter ever included within them, and that includes most of the metals that are ever produced by stars, binding them within the hot diffuse intracluster medium. And what that means is that if we make measurements of cluster metallicity, this reveals the integrated history of star formation and metal enrichment processes over the course of billions of years up to the time at which we observe these individual systems. In particular, X-ray measurements of the hot intracluster medium are able to trace out the spatial distributions of these heavy metals. And I'll get a little bit more into this in a second, but the near uniform distribution of heavy elements that we see within the universe inside clusters directly point to highly energetic mixing and distribution processes, which we believe are linked to active galactic nuclei. So to tie all of this up in a nice little bow, chemical measurements of the intracluster medium provide a direct probe of star formation and AGN activity throughout the history of the universe. Diving a little bit deeper into this early enrichment scenario and highlighting previous work done by KIPAC alums, such as Norbert Werner, Andre Urban, and others. If we make metallicity measurements of clusters outside of the cluster cores in the local universe, we see remarkably constant enrichment at a value of about 0.3 solar. And this is true within a cluster, azimuthally, between systems in the local universe, and extending out to a redshift of about 1.5, with little to no evidence for the evolution of cluster metallicity. And so if star formation and AGN activity really do peak during this period of cosmic noon between a redshift of about 2 to 3, then we require measurements of cluster outskirts outside the cores at high redshift to really probe the evolution of metallicity over the history of the universe. Looking a bit at the current state of the art, so I've combined X-ray data for about 20 plus megaseconds from Suzaku, Chandra, and XMM Newton. And just now we can just begin to see evidence for decreasing metallicity as we approach a redshift of 2. So this is a figure from a metallicity paper that I published, and just focusing here on the red and blue band. These are power law fits to X-ray data, cluster metallicity beyond the cores. And really what we're just looking for here is, are things consistent with 0? Are we seeing any evidence for decreasing metallicity with redshift? And for the red band fit to the X-ray data up to a redshift of 1, we are still very much consistent with no evolution. We are not seeing any evidence for decreasing metallicity with redshift. And just including the high redshift data points in the blue band, we are just beginning to see evidence for decreasing metallicity. And so this brings up the question of needing deeper, higher redshift data to make better measurements of clusters at higher redshift, where the weighting for these fits will be more important, and coming up with more descriptive models so we can actually describe the physical processes going on rather than just saying, is metallicity decreasing? What evolution do we see? And so this requires us really to think about the next generation, because current X-ray flagships are reaching the limits of what they can produce for high redshift clusters. Chandra is not sensitive enough to probe beyond the cluster cores, while the spatial resolution, the point spread function of XMM Newton, makes spatially resolved studies of clusters very difficult and is exceptionally prone to point source contamination. Joint studies of clusters using both observatories have been fruitful, but going forward, this requires set coordination between the satellites and extremely high exposure times to get the statistics that we need. So I won't go into full details. Sven gave a very nice introduction to upcoming potential X-ray missions, but I'm particularly invested in AXIS, the Advanced X-ray Imaging Satellite, just to say that its high sensitivity, stable point spread function across a wide field of view, and low particle background due to its low Earth orbit uniquely combine to make spatially resolved studies of clusters possible. And, oh, there seem to be some formatting issues here, but just to highlight some of the power of Axis, 3 megaseconds of Axis data split across 30 clusters, redshifts of 1.5 to 3, are going to provide unprecedented constraints on cluster metallicities, both for individual systems and in statistical ensemble. And what should be showing up here is both a blue and red band that reflect a new physical model that we've been trying to come up with that uses the cumulative history of star formation in the universe, sped up by the presence of AGN in the early universe to really unveil the role of AGN feedback. And the simulations that I've made for the power of Axis at high redshift really hammer home how transformative the next generation of X-ray instruments will be. So I'll leave up a few points of my summary, but I'm hoping that I've convinced you that the current state-of-the-art X-ray measurements are just hinting at the evolution of metallicity in the early redshift, and the next generation of X-ray instruments will truly be transformative in this space. I'm happy to take any questions.
Okay, thank you, Anthony. Do we have any questions? Shantakriti.
Hi, yeah, nice talk. And I should have probably known this before, but I didn't know that Axis is supposed to be a low Earth orbit. So for example, with Suzaku, the problem was that because of being a low Earth orbit, satellite, it had very high contamination from fluorescent lines of nitrogen and oxygen in the atmosphere. So is it going to be a problem for Axis?
That I am not sure of, and I'm trying to think of the context of these measurements. What energies are those lines at?
These are all soft X-ray, like starting from 0.6 keV or below.
0.6 keV. I don't know what mitigation has been done for that. I assume the fluorescence lines in Suzaku were coming from the hardware itself. No? Were they coming from the atmosphere or atmosphere? Then I don't know of the specific mitigation efforts that Axis has done to do that. I'm hoping that's reflected in the background models that I've been using, but I don't know at this time.
Thanks. Any other questions? Greg.
So I was wondering if this very minimal evolution that you see at low redshifts, if this is consistent with what is seen in cosmological simulations?
I will say no, because cosmological simulations had not predicted this. In fact, cosmological simulations predicted extremely low cluster metallicities, and it wasn't until the results in the past decade from X-ray observatories in the local universe that they turned up their AGN feedback to match the metallicities. So no, it's not reflected, or it wasn't.
Okay, thanks.
Okay, and Roger.
Okay, thank you. This might have to be a longer conversation, but is your sort of qualitative picture of what's going on, that the enrichment in the outer parts of galaxies is the resident galaxies having the gas stripped out of them and put into the cluster, or is it the gas that is joining the cluster from galaxies around and going through an accretion shock and so on? Which, do you have a sort of picture as to which of those two is more important?
So the picture here, especially due to the azimuthal symmetry, the gas is most likely pre-enriched when it's coming and accreting onto the clusters. But that gas had to be enriched in some way. So really the picture that we're looking here in terms of early enrichment is the metals being produced within the host galaxies, being blown out to extraordinary spatial distances by the AGN in the early universe, and then accreting back onto the cluster as it grows. Yes.
Okay, well, thank you, Anthony.